Hello, my name is Josh Urban Davis from Dartmouth X Discovery Lab, and today I will be discussing our work on TangibleCircuits, an interactive 3D printed circuit education tool for people with blind and visual impairments. In the maker community, novices learn circuits with breadboards by following examples and tutorials from the web. However, most of the existing web tutorials are inaccessible to blind or visually impaired BVI community because they rely heavily on visual information to communicate the material. The high bar of entry to learning electronics excludes the BVI community from participating in innovation via making. Furthermore, BVI children also miss out on critical STEM education and further high-tech careers. And while many accessibility tools exist, most do not encourage or enable BVI users to create their own accessibility tools. To account for this, we created TangibleCircuits, a cost-effective, tactile model of a breadboard circuit with audio feedback for BVI makers and students. TangibleCircuits comprises an automatic parsing tool, which translates a circuit diagram in the Fritzing format into a 3D model that is printable with a commercial 3D printer and protopasta composite conductive PLA material. The tactile circuit model has components printed using conductive filament and can be affixed to a smartphone to allow for touch-based interaction for learning. When each component or wire is touched, audio feedback details the name of the component, the position, and other details regarding its connection and implementation. I will give a brief demo of our system in action.
This is wire line 5. It connects a wire line 6 to an NPN transistor. This is NPN transistor. This component should be inserted into pin 19J, 20J, and 21J. This is wire line 5. This is wire line 5. It connects a wire line 6 to an NPN transistor. This is NPN transistor. This component should be inserted into pin 19J, 20J, and 21J.
This work builds upon many previous intersecting research ventures in the design of circuit prototyping and education tools, tangible interaction approaches for BVI persons, and STEM education tools for BVI students. These previous efforts indicate that novice engineers often learn circuit prototyping through replication of example circuits and face numerous challenges including choosing correct components, wiring components together, and debugging. This problem is further compounded for students with BVI due to the visual nature of our traditional teaching methods. Many tools and approaches have been developed to assist novice students with BVI learn STEM-related skills by incorporating audio feedback. While many of these tools have been designed to teach programming, none have explored techniques for teaching physical computing. To better understand this problem space, we conducted a series of semi-structured interviews with 3 BVI engineers and students familiar with circuit prototyping technology. We first wanted to understand current practices in hardware education and found that web tutorials were often relied upon by our interviewed instructors. Literature corroborated this insight, revealing that web tutorials were commonly used by educators of a variety of backgrounds as a principal source of classroom material. We also inquired about current tangible methods used within this domain, and found that tactile diagrams were commonly used, but due to the abstraction used in direct graph translation, these diagrams remained largely unusable. Finally, we discovered that existing circuit education tools for producing tactile assets included braille embossers and swell paper, which are prohibitively expensive and not commonly available in engineering educational settings, unlike 3D printers. It is for this reason a 3D printed tool seemed like a viable solution to mitigating this accessibility limitation.
Wireline.
It seemed evident to us that we needed to better understand the current limitations of web tutorial accessibility, so we conducted a formal study. The focus of this initial study was to understand the magnitude of accessibility limitations within online open-source tutorial platforms, as well as gain insights into common web accessibility pitfalls. For the purposes of this study, we collected 7,321 online tutorials from 2 popular online open-source tutorial platforms, Arduino Project Hub and Fritzing Hub. We then filtered these tutorials for incompleteness or other severe problems with their implementation and resulted in 3,909 tutorials. We then analyzed these tutorials using the Web Content Accessibility (WCAG) online protocol, which is a guideline system for ensuring web accessibility. This figure details some of the findings from our analysis. The purple bar indicates the number of Arduino Project Hub tutorials containing a specific kind of media detailed on the right, while the green bar reflects this same information for Fritzing Hub tutorials. Overall, we found the majority of tutorials were woefully lacking in information to make them accessible to people from the BVI community. For example, we found that a large portion of these tutorials contained visual graphics, but very few actually contained any sort of captions or alternative text to detail what was going on inside these graphics. Many didn't even include step-by-step instructions to allow the completion of the circuit. In fact, only 2% of the tutorials surveyed met WCAG standards of accessibility, indicating a significantly limited accessibility to the majority of these online tutorial platforms. Informed by the insights from our formative studies, as well as our literature review, we comprised a series of design considerations to guide the development of systems to mitigate these accessibility limitations. A system should provide adequate information regarding components to ensure their identification and recognizability. A system should incorporate multiple forms of feedback and guidance, such as audio, tangible, and others, in order to broaden accessibility. A system should support understanding of the structural and spatial information of the circuit, including connectivity of different components and their interactions. And finally, a system should employ automation to mitigate the considerable time and effort demanded of tutorial designers and educators to meet these standards of accessibility. Based on the previous design considerations, we developed TangibleCircuits, which I'd now like to walk you through. TangibleCircuits takes a Fritzing diagram as input and parses the diagram into a 3D model and touch-based audio interface. These two complementary components comprise our tutorial system, and the resulting interactive tactile diagram operates on a commodity capacitive touchscreen device, such as a smartphone or tablet, without any modification necessary to the device. The 3D model is extracted from the Fritzing diagram and renders an approximate replica of the component within the circuit. TangibleCircuits components and wires are printed using protopasta composite conductive PLA hard extrusion filament. The conductive filament is crucial to the operation of the device. Although the case and breadboard are printed using non-conductive filament and the components printed with conductive filament, both these elements can be printed as a single unit using a multi-material 3D printer. The audio interface consists of a series of buttons laid out on the display of the touchscreen device. Each button is associated with a different component present within the circuit diagram. When touched, the device reads audio information related to the target component associated with the button. The casing allows the tactile circuit diagram to sit above the capacitive touchscreen. Each component in the tactile circuit diagram sits directly above its corresponding audio interface buttons, and thus triggers the voice annotation below each component when touched. The resulting interaction allows for both audio and tangible interaction to inform the user of the circuit's spatial, structural, and geometric information. Once again, I would like to provide you with a brief demo of our system being used.
This is buzzer. It connects 220 ohm resistor with a red LED and an NPN transistor. The red power wire of this buzzer should be inserted into pin 11F. The black ground wire should be inserted into pin 13F. This is red LED. It connects wire line 3 with a buzzer and an NPN transistor.
In order to understand the effectiveness of TangibleCircuits for assisting BVI users at understanding sample breadboard circuits, we conducted a formal user study. The focus of this evaluation was to understand how Tangible Circuits complements and contrasts open-source web tutorials at communicating circuit tutorial implementation.
This is buzzer.
We recruited 14 participants, 10 of which identified as female,
It connects 200
8 self-reported as blind,
20 ohm
and 11 self-reported their electronics background and familiarity as none.
resistor with a red LED.
Our study consisted of 2 sessions, learning and testing, as well as 2 stages, Tangible Circuits and web tutorial.
LED and an N.
In the learning session, participants were asked to learn one of 4 sample circuits,
PN transistor.
using either Tangible Circuits or web tutorials modified to meet WCAG accessibility standards. I pause to emphasize this point here. We didn't want to construct a straw man argument for our comparison, since we largely knew that tutorials that did not meet WCAG standards of accessibility would not be usable by this community. So we only chose to compare Tangible Circuits with web tutorials that had met WCAG accessibility standards. The testing session followed the learning session immediately, in which participants were asked
The red power
2 tasks, a component identification task and an error identification task.
wire of this buzzer
During component identification, we presented participants
should be inserted.
with a bucket of 17 common electronic components such as resistors, LEDs, and others. The bucket contained only one example of each kind of component. We then asked participants to use their stage apparatus, either web tutorials or Tangible Circuits, as a guide for identifying components used in the construction of the tutorial circuit.
Into pin 11.
During circuit error identification, we presented the participant with a completed circuit using physical components on an unpowered breadboard, such as the 4 displayed here. Each of these physical circuits were similar to the circuit described in the tutorial apparatus, either web tutorial or a Tangible Circuit tutorial. But the physical circuit contained 2 errors, a wire error and a component error.
The black ground.
Participants were then asked to use the tutorial apparatus as a reference for answering 3 questions regarding the physical circuit.
Wire should be inserted
1. Is this physical circuit the same circuit described in the tutorial?
into pin 13.
2. If this circuit is different, how so is it different?
F.
3. How would you modify this physical circuit to match the circuit described by the tutorial?
This is red LED.
In the component identification phase, participants were able to identify 62% of the circuit components with Tangible Circuit apparatus versus 34% with the web tutorials. Furthermore, 3 participants who completed the Tangible Circuit stage first were able to correctly identify the resistor component, but unable to do so when subsequently completing the web tutorial stage. This indicates that overall, geometric information of the components was better recovered by participants using Tangible Circuits than web tutorials. We found that overall, participants performed significantly better using Tangible Circuits than web tutorials at identifying the circuit errors. For more details on these results, and in the interest of time, please refer to our paper.
X wire line.
We also collected Likert results in order to gain a sense of the subjective experience of our users when interacting with our prototype. We found that overall, on a scale of 1 to 5, participants found Tangible Circuits to be less confusing, less frustrating, and more helpful for understanding information than web tutorials.
3 with a buzzer and
To briefly summarize, interactive 3D printed interfaces can assist students with blind and visual impairments, and Tangible Circuits assist students in understanding circuit structure and identifying circuit components.
an NPN
We identified a number of potential future avenues for investigation within this domain of research.
transistor.
While our user evaluation focused on students with BVI, we would like to broaden this study to participants without BVI. Because our system was designed using a universal design approach, it's necessary to understand how students without BVI might also interact with this system. A universal design approach would ensure its greater and wider adoption, and corroborating the results found from our BVI user study with a non-user BVI study would help to encourage its wider adoption and use. Our study also focused on small, simple demo circuits, but we also believe our system could be scaled to more complicated circuits as well by decomposing large complicated circuits into smaller modular circuits that could be completed and then wired together to create larger, more complex systems. And finally, we would like to find additional use cases for this 3D printed tangible system. Once again, this has been Tangible Circuits, an interactive 3D printed circuit education tool for people with visual impairments. I'd like to thank my collaborators, including Emily Whiting, Daeyeon Woo, and Jindong Yang, and I am Josh Urban Davis. If you have any questions, please feel free to reach out to me at the email address listed or on Twitter. Thank you for your attention.